Well, hello. This is Mr. Meyer coming at you from the South Way Happy Studios here in Livermore, and we are going to talk about vectors. So let's talk about them. Now, first of all, what the heck is a vector? Let's have this guy explain because he does a good job.
Hey, I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
Oh, yeah. So let's talk about this, right? We got vectors. So a vector, like you said, is an arrow. Its standard position will start at the origin and it will shoot off somewhere and hit a point, and that will be the end point of that vector. Sometimes I call it the tip, sometimes I call it the head, so watch out, I get a little crazy there. And that vector will have both direction and magnitude. So direction will be the angle that we will measure it at, and magnitude will just be how long that line is. And that's all a vector is. So now let's get into all the vocab that you need to know about a vector. Vectors are usually written in what's called component form. Now, component form just means that I'm going to give you the tip of that arrow. So let's just for fun say that this was over 5 and up 2. The component form of this would be 5 comma 2. And notice we use brackets to let you know it's not a point. We use those, that looks like a less than greater than sign, right? We use them to let you know it's a vector, meaning it's starting at the origin and it's ending at 5, 2. A and B are called, these two things are called the components of the vector. And so that's really one way of writing vectors. The zero vector I have written here is just the zero vector sometimes shows up, kind of rare, but it has a 0 magnitude and no direction. Now let's talk about how you can find a vector. So down here you see head minus tail. And the head minus tail rule, sometimes I call it the tip minus tail, is when someone gives you points. So you got to be very careful. Is somebody handing you a point? Because if they are, then you need to subtract those 2 points. You have to do the tip minus the tail, or the head minus the tail, to get it in vector form. Remember, vectors will be sitting at the origin and be shooting off to a specific point. We got to keep the magnitude, we got to keep the direction, and so therefore you just do a little tip minus tail and you will be able to find out what that vector's component form is. Also, if you have more than one vector, we call them equivalent if they have the same magnitude and the same direction. So let's see, what am I talking about here, right? Let's look at this example. I want to prove that vectors RS and PQ are equivalent. Now notice those are points. Notice they have parentheses. They do not have the vector notation. So I'm going to first try to write them as vector notation. So, even think about a graph real quick if I could. I could be like, hey, look, here's graph paper, and this is going to be ugly, but let's try. R is negative 4, 7, so 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 is right here is R. And S is going to be negative 1, 5, 1, 2, 3, 4, 5. So there it is. There's S. And so this goes from R to S, so it would look like that. I'm going to put a little arrow over there because that's a lot of times how people write vectors is they put a little arrow over it. A little ray kind of looks like geometry. Same thing with P and Q then. So then we would start at P, which is 0, 0. There's P. And then Q would be 3, negative 2. And if these two vectors are truly equivalent, then they should have the same magnitude and the same direction. Well, let's go. Let's notice what we could do here. We're going to mess around with R for a minute, and I'm going to take R and I'm going to move it to the origin. So how the heck would I move it to the origin? Well, I would have to move it right 4 units, and I would have to move it down 7 units. So I would have to move it right 4 units and down 7 units to get R to sit at the origin. Well, that means I would have to do the same thing to S, right? I would have to move it right 4 units. So if I moved it right 4 and I moved it down 7, what would the new position of that thing be? Well, right 4 would put it at 3, and down 7 would put that at -2. So that would be the new coordinates of our S. And notice that you could have gotten that just by subtracting them. And that's what I was trying to say up there in the highlighted head minus tail, tip minus tail rule. If you know which one's the tip, in this case S, do tip minus tail. So if I want to know vector component form of this, I would just do -1 minus a -4. There's the tip, the x coordinates of the tip minus the tail. Now I will do the y coordinates. I have 5 minus a 7. And if you notice, that would just turn into 3, -2. That would be your vector. So that vector would have those endpoints, that endpoint, starting at the origin and ending at 3, -2. Well, since I've already graphed this guy, you already know the big surprise, right? If we do tip minus tail for this guy, we would have 3 minus 0. We would have -2 minus 0. Oops, don't know where that comma came from. And I would have 3, -2. And that would be component form of the PQ. So each vector would have the same component form, therefore they're equivalent. And we could even count their slopes if we wanted to. We could do rise over run, count the slopes, and see the slopes are the same. They have the same endpoint starting at the origin, so their magnitudes are the same. Or we could use, to find their magnitudes, we could use the distance formula from R to S and get that. So there's many ways to prove that vectors are equivalent. And I should probably mention some of the ways you will see us write vectors is a lot of times, let's call this vector U. I could go a U with a little arrow over it. If we type it, sometimes we make it, it's hard to do, but we make it a bold U, and we would call that a vector. So it's just different ways that people can write vectors. Now let's talk about magnitude, because I kind of mentioned it. Magnitude of a vector, also known as the absolute value, because it's the distance from 0. So if you're starting at the origin and you're measuring how far something is, you know, that's the distance from 0. That's the absolute value. That's why it's denoted by absolute value bars. But it really means magnitude. It doesn't mean make the whole vector positive or something. It means tell me the magnitude. How long is that line? So distance formula is your friend right here. Here's distance formula. If I give you 2 points, you can just subtract those points, and then you could square them, and then square root it, and you get that distance from one to the other. That is the magnitude of the vector. Here's kind of a key note, though, if you notice this part. I think a lot of people don't even notice how simple it can be, is that if you take into account that you will write that vector in component form, then you can just square their components and add them together and square root it, because it'll be starting at the origin. And so that usually makes your life pretty easy. But let's do one. So here's an example. You got point P and you got point Q. So again, there's 2 things. I'm going to find where this thing is. So -2, 2 is right there. There's P. And we're going to go to Q. I should put a little arrow over there so I know which one's the tip and which one's the tail. And I'm going to go to Q, which is 3, 4. 1, 2, 3. 1, 2, 3, 4 right there. It's going to go from P to Q. So there it is. All right. Now, if I want to know this thing in component form, I have to move P to the origin. And so what some people will say is, hey, just move P right 2, down 2, and it'll be sitting at the origin. So if I do that, I also have to move Q right 2, down 2. And where will that put it? Well, that will put it at 1, 2. So, I'm sorry, right 2 would be 5, 2. So 1, 2, 3, 4, 5, 2, boom. There it would sit at 5, 2. And since it's coming out of the origin, I can call it a vector, and there is your vector. Now look, they should have the same magnitude. They should have the same direction. And it looks like they do, right? It looks like they're both going the same direction. It looks like their magnitudes are the same. In fact, what is that magnitude? Well, now I have it in component form. I can just say, hey, it's 5 squared plus 2 squared, square rooted, or root 29. And that is the magnitude of this vector. Simple enough. Nice work. Now let's go on to vector operations. Now vectors are, the fun thing about vectors is you can have more than one vector and you can do some basic algebra with them or arithmetic really. You can add vectors together and therefore you can also subtract them. You could just add their components together. If they're in component form, you just add their components together. You get a new resultant vector that tells you what's going on. And that's going to be really valuable in a lot of stuff we do. There is also scalar multiplication, which means kind of the distributive property. You would have a number out front, or you want 3 times one vector, you would just multiply the components by 3. So let me show you a little quick example here. You can see that I have vector u is defined as this, and notice I know it's a vector because of component form using the what looks like a less than greater than sign, and also vector v right there is 2, 4. So that means both of those vectors are starting at the origin and they are going to those respective endpoints. Now if I want to find out what 3u is, then I'm just going to take 3 times vector u and I will get a new vector which will be negative 3, 9. And that's the endpoint. Again, starting at the origin and ending here, that would be our new vector, or our vector that's 3 times the magnitude, or 3 times u. U plus v. We will do this a lot. You'll have 2 forces acting on something and we will have to add them together and find the resultant. But really good news is if you have them in component form, there's u. If I'm going to add it to v, then it's really actually kind of as simple as you would hope. The new resultant vector, 1, 7, right? And so again, starting at the origin, going to 1, 7. And that's what that resultant vector would look like. What if we have 2 u's, or the opposite of 2 u's, meaning you got to change all their signs and double it, and then add that to 3 v's? What would that look like? Well, just break it down into 2 steps. So if I'm going to do negative 2 times the u vector, which was 1, 3, plus 3 times the v vector, which was 2, 4, I would have 2 comma negative 6 for the 2u vector, the negative 2u vector, and 6 comma 12 for the 3v vector. Add those bad boys together and you get 8 comma 6, and that is your resultant of that operation. Now the key here to understand is that this middle one that I want to kind of show you real quick is that this is going to happen to us a lot in vectors. We're going to have one vector which is at negative 1, 3. So it's going to look like this, right? There's negative 1, 3. We're going to have another vector that's at 2, 4. 2, 1, 2, 3, 4. And it's going to look like that. And the resultant vector is when those 2 vectors are added together. And that's like an airplane traveling and then the wind's blowing it, or something like that. And there's a couple of ways that people will do this addition visually. You can move like that blue vector. You can move that vector to the end of this one. Make sure it's going the same direction and magnitude as the original blue one, and you can try to figure out where that point is. Or some people will draw a complete parallelogram and they will find out the resultant vector is this guy cruising through here. And that resultant vector, the 2 added together, that's where this plane's going to travel, or whatever this represents. And in our case, it would go to 1, 7. And so just a little visual of what you might see of things to come. Now what about unit vectors, right? You got a unit circle that you did last chapter. And so unit circles, we knew that the radius was 1. Well, guess what? A unit vector just means that the magnitude is 1. So how do you make a magnitude of 1? How do you restrict it? Well, how do you do anything? If you have a length of 10, how do I make it a length of 1? I just divide by 10, right? I just divide by whatever you have. And then I give you 10 of those, and now it's the same length. So that's all we have to do here on vectors. If somebody gives me component form of a vector, and I know the magnitude is m, then I just divide both of those pieces by m. It'll be going the same direction, and its magnitude will now just be 1. So that's the end of the story, right? That's all a unit vector is. So officially, if you look in the book, it'll look like this little equation right here where they say take v, vector v, that's supposed to look bold, and put it over its magnitude and you're good. So that's just what it looks like. So let me show you one of those. A unit vector. So I give you a vector. I want the unit vector in the same direction as negative 2, 4. So what do you need? You need the magnitude, right? So if I want to find the magnitude of u, then all I have to do is square root, is that negative 2 squared plus 4 squared? So 4 plus 16, is that root 20? And root 20, if we want to clean that up a little bit, is 2 root 5. And so there is the magnitude. So now to find the unit vector, we just put each one of those guys over their magnitude. And there is your new unit vector. Right? I guess I could clean that up a little bit. Looks to me like negative 1 over root 5, comma 2 over root 5. And there is the unit vector that would be going the same direction but would have a magnitude of 1. Now, there are two very important unit vectors. There is one in the x direction and one in the y direction, but now with vectors, instead of calling this x and y, we will now call this I and j. Right? So I is traveling horizontally and j is traveling vertically. Those very important unit vectors, the I vector is 1, 0. That means it's 1 unit going right, and j is 1 unit going up. And those are our unit vectors. And the reason this is important is because the fact is that you can write vectors another way. I've shown you component form, and I said, you know, like, hey, 3, 5, that's component form of a vector. Well, you can also write it as the sum of unit vectors, or the linear combination way, which means it would be 3 I vectors plus 5 j vectors. And that's it. It's nothing fancy. It's just saying I could write it either way. Some people prefer component form. Some people prefer the sum of unit vectors form. And you never know which one you're going to get. They mean the exact same thing. So if you don't like one form, just rewrite it in the other form, unless it specifically states. So like here's an example. They say, let u be a vector with this initial point and this terminal point. Sounds like tip minus tail to me. So if I'm going to do tip minus tail for that, I will have to do, looks like negative 1 minus 2, comma 3 minus a negative 5. There is my component form for vector u, right? Put a little arrow over it. And so what would that look like? That would look like negative 3, comma 8. And now if I want to write that as the sum or the linear combination of it, it would be negative 3 I vectors plus 8 j vectors. So just two different ways to write the exact same vector. And I can still ask you magnitudes, and I can still ask you stuff like that. In fact, let's take a shot at that. All right, there's also another way to talk about vectors and how to find their direction and their magnitude. And that goes back to your good friends at trig, right? So look at my drawing right here, and this vector, it has an angle theta and it has an r value, and whatever that magnitude is. And the endpoint right here is x and y. And I would really love to find the values of x and y. So look at this. If we just pull a triangle down, we have the x direction, we have the y direction. We should be able to solve for those. In fact, because of our trig that we know, I could say something like, to find, let's do x, right? So here's x, and let's use the cosine of angle theta would equal x over r. But if I want x by himself, I'm just going to go ahead and multiply r to the other side and say x is equal to r cosine of theta. And that is actually true all the time. In fact, remember your unit circle, the r was 1. Remember the x value was the cosine and the y value was the sine? That's going to run true here too. In fact, let's try to find y. To find y, I would do sine of the angle is equal to y value over r. If I wanted y by himself, I would get y equals r sine of theta. And notice you have a way of, if somebody gives you direction and magnitude, you could find the component form. You could figure out what x and y actually are of that vector. That's something you need to memorize. I hope this isn't anything too spooky. It'll be a pretty easy thing to memorize, and I think you can do it. So that would be awesome. Let's try this down here. Example that says, let's sketch one that has a magnitude of 41 and then the direction of 220. So I'm going to kind of give myself a visual of this. I'm like, all right, I'm going to start in the direction of 220, which is like somewhere down here. And so this is my 220 degrees. And my magnitude is 41. I will just label it like that, magnitude of 41. Beautiful. Now I'll find the component form. In other words, what the heck is this value right here, right? What is that when you fill in those numbers? Well, as you see from our equations up there in the green, you just say, well, x is equal to r cosine of theta, which means magnitude cosine of 220. And I can tell you what the x value will be. And then I can tell you the y value is r sine 220. And so, oops, guess I could have put the r value in, 41 sine 220. And then I will be able to give you the component form of both of those. So I should probably check my mode. I am good. I'm in degrees. So 41 cosine 220 and 41 sine 220. And I get negative 31.4 comma negative 26.35. So negative 31.4 comma negative 26.35, I think I said. Let me double check. Yes, and that is component form of our drawing. And notice I like the little drawing because I can see that the x and the y, they are actually in the negative direction, so it is left and it is down. And so I'm feeling like, wow, I did a really good job representing that vector right there. All right, what about going the other way? Could I give you a point and you could tell me the magnitude, the direction? Yes, again, with our love for trig, we should be able to do this. So 0.34, 1, 2, 3. Remember, this means it's a vector, starts at 0, and it means it goes right 3 and up 4, so it looks exactly like that. So there is my vector, right? The cool thing that I know, this is 3, I know this is 4. Little a squared, b squared, c squared is going to tell me this is 5, so I already got the magnitude. And now all I need is the direction or the angle right there. So starting at 0, let's measure that angle. And so, you know, you could pick sine, you could pick cosine, you could pick tangent. Most people will pick tangent for the angle. They'll say the tangent of the angle is 4 over 3, which means I got to figure out who has an arctan of 4/3. And so now I will grab my calculator one more time and I will say, tell me what angle has an arctangent of 4 over 3. And it says about 53.13 degrees. So there you go. I know the magnitude is 5, and I know the angle, the direction, is about 53.13 degrees. 53.13 degrees, and I have given you magnitude and direction of a vector. Beautiful. Let's have you give it a try, and then we'll try some bearings problems. All right, and excellent work again. Now let's talk about some uses of vectors here, and let's talk about a bearing problem, which hopefully you remember your bearings. Remember, north was 0 degrees, and you go clockwise around to graph it. But that's going to be confusing because vectors we're going to do standard position. So we got to be a little careful. So we got an airplane whose bearing 335 degrees. How would you show that as a drawing? Well, it's not too bad. Again, you got to figure out where 335 degrees is. So remember, this is 0, this is 90, this is 180 on bearings, 270, and all the way around, obviously 360. So this airplane's going 335. It's going like somewhere out this way, right? So this is 335 degree bearings. And he's going at 530 miles per hour, so that is the length of that line, the magnitude of that line. And so we want to get component form, which means I would really just like to give the two components of this. Well, we know our formula, right? X is r cosine theta, y is r sine theta. The only problem is we don't really know what theta is. Or do we? I guess we could do some quick math to figure out what theta is. So since we know the bearings were 335, that means that this little chunk right here from 335 to 360 has to be 25 degrees. And we know that this is 90 degrees, so I'm feeling pretty good. Our x-coordinate would be r cosine theta, or 530 cosine, was that 115? And our y value would be 530 sine 115. And now you can just go ahead and grab your calculator and have it do all the work for you. So 530 cosine 115 and also 530 sine 115. And we got negative 223.99. So negative 223.99 and 480.34. 480.34. So there's my component form, right? Negative 223.99, comma 480.34. And those are the two components that make up this plane's traveling, right? It's traveling, in essence, left, negative 200 miles an hour, and it's traveling up 480 miles an hour. And so together, those two vectors combined will get you the one that's actually doing of 530 miles an hour at a bearing of 335 degrees, or an angle of 115 degrees if you want to talk about it in standard position. Now, what does that help us with? Look at the next example. We got an airplane flying, and we got wind blowing. And so the question is going to be, you know, where's the plane going, right? We want to know where they're headed if this is happening, because then they're going to be off course because of the wind. So again, I'm going to try to draw this picture. Like, all right, I noticed that the airplane has a bearing, what is that, of 325. So it's going really fast. So 325, it's going to be 325 miles an hour. So it's going pretty quick at a bearing of 340 degrees, which tells me that this angle right here is 20 degrees. Right? Because again, bearing starting at 0 north. Now I'm going to take a different color. I'll take red, and I'll do the wind. Now the wind is only 40 miles an hour, so that's not too much. That's just a little arrow. But it's going at 320 degrees. So that means that this is 40 degrees right here. Well, now I got two things that I can do for component form, right? I know their angles. Now remember, component form, we got to start our angle at 0 degrees and measure all the way to here for the airplane. So for the airplane, so I guess I'll do, you know, x for the airplane. That would be 325 cosine of 110. And the y of the airplane would be 325 sine of 110. And so if I grab my calculator, I can give you 325 cosine of 110, and I can give you 325 sine of 110, and the component form of that, negative 111.16, negative 111.16, comma 305.4, and there is the components of the airplane, right? Now what about the components of the wind? So the wind has its own components that we can take care of. So the x for the wind would be, how fast was the wind going? 40 miles an hour. So that is 40 cosine of 130. And the y for the wind would be 40 sine 130. And so component form for that guy, just grabbing my calculator one more time, 40 cosine 130, 40 sine 130. And you see that as negative 25.7 and 30.64. So negative 25.7 and 30.64, I think I said. Yep. And that is our component form for the wind. So they have two different components. Well, what's the actual speed and direction of the plane? Well, the plane is going to benefit from the wind, right? It's going to be not only the airplane, but it's also going to be the wind. We're going to add those two things together. So now we just have to add the negative 11116, comma 305.4. Add that to the negative 25.7, comma 30.64. And you have the component of both the wind and the plane, which in essence is really the plane, right? Again, that weird thing about the way people do this is sometimes you will see them draw that red vector. They will kind of throw it onto here at the end, and then they can find the resultant vector as that guy. And that's really what you're doing. You're finding this bolded green line. I want to know its direction and its magnitude, and that's what I'm doing when I'm adding these two vectors together. So yuck, I got these really gross numbers. Negative 111.16 plus, I guess, a negative 25.7. So 136.86, negative 136.86, comma, and now what do we got? Oh, what is that? 335, 336. So 336.04. So that is the resultant of the wind and the plane together. And now if I want the magnitude of that, remember I just square them both, add them up in square root. And if I want the direction, I will just do probably the arctangent of that. Because remember, here, now that we found the x and the y, we know that this is negative 136.86. We know that this is 336.04. And so I should be able now to find those, and I will find those right now. Well, of course, something interesting happened when I typed this in my calculator. Magnitude was not a big deal. Squared them, added together, square root. You can see that at the top of my screen was 335 on my calculator screen. And that's miles per hour. That's how fast the plane's going. So we know the plane was going 325. Well, the wind's pushing it a little, so it's going a little faster. So they're going to get there a little early, unless they're off route. Now, the next thing you notice was then I just went into arctan, and I wanted to arctan the opposite over the adjacent. And I typed that in, I got negative 67 degrees, and I was like, oh, that might freak some people out. So remember, that's like a reference angle. That's negative 67 degrees, makes sense. But it's down in quadrant 4, and so we now have to move that over to quadrant 2 where this plane is actually traveling. So all I did was take the 180 and I minus the 67 degrees to find out where this plane actually is headed. And you'll see the angle is 112. So I just didn't want that to surprise you if you saw that the angle was 112.16. So the angle is 112.16 degrees. And there you go. I know exactly how fast the plane is going, and I know exactly what direction it is headed, and therefore I can tell you, where that plane will end up. In fact, it would probably be fun to do it in bearings rather than degrees, or rather than standard form of an angle. So maybe that will be something we'll try in class. So you guys have a good day, and we will try to mess around with vectors, and I will see you tomorrow. Stay happy.